Okay, so today is the last day where we're not doing Fourier transform, we're doing information coding. We'll be back to it next time. So last time we talked about error correction codes, and I gave an example of the Reed-Solomon codes, which we find in all of our technology. And I just showed you like the details of how they're set up to work. But we didn't look at any of the actual math of how these error correction and error detection codes can work in the first place. It was just left as sort of a magic trick. So now let's actually look at some specific examples of how you would create redundancy in a message in order to allow yourself to be able to detect or correct errors. Okay, so first we'll start with just trying to detect errors from a sequence of bits. So suppose that all we wanted was to detect a single bit error. Then actually there's a very simple strategy using a parity bit that allows us to know whether we have one bit of error. Okay, so suppose you have some information bits. Something like this. Let's say we have 7 bits of information. All right. And we want to add one more bit of redundancy in order to allow us to detect if there's an error. Well, what you can do is you can let your one bit, you can set the one extra bit so that the number of ones in the sequence is even. Okay, that's easy enough. It's already even here, so I'll set it to be 0. If it was odd, I would set it to be 1. So that's the idea of having a parity check bit. And clearly, we can tell if there's 0 or 1 errors here. If there's 0 errors, the parity is still going to hold. And if there's 1, then the parity doesn't hold, so we detect an error. Of course, if there's more than 1 error, then we're back to not knowing if there's an error. So this would just detect up to 1 bit of error. So we call this a parity check. And one way to write it is that you have a sum of all the bits mod 2. So that means the sum after dividing out or subtracting out all multiples of 2 equals 0. So put a question mark here to say you check whether that equals 0. It should equal 0 if there are no errors. Right? So the capabilities of this type of a code, it cannot detect 2 errors. Or in general, it can't detect any even number of errors. Right? And so it can detect odd number of errors. So for those, let's say this is even. Let me mention, it looks like we have at least a couple of visitors today. We've got some high schoolers on spring break. That most of the topic of this class is on signals and splitting them up into sinusoidal components and doing analysis on them that way. But we're taking a little sort of a break from that and looking at encoding of information and how you compress, and in this case, how you allow yourself to correct for errors. Okay, so this is detection. That was kind of fun, but maybe not quite as magical as correction. Okay, so this allows you to say, yes, there was an error in there. I can't recover, but at least I know when there was and when there was not an error. I can declare this to be an erased sequence. All right. Correction is a little more magical because you actually go and identify where the error happened and fix it. So for this, we're going to look at, first of all, the simplest case. The simplest code that's not very magical, it's pretty obvious, is repetition. Okay, so a repetition code just means take your information bit and repeat it a number of times. For example, a repetition 3-1 code means you just take your one bit of information. So we would say 3 is how many times you repeat it. 1 is how many information bits. And that just means repeat the bit 3 times. In whatever, if this was memory, repeat it in memory 3 times, in case you're worried about bit errors in your memory. If you're transmitting it, just repeat the transmission 3 times. And then to decode this, decode the majority. So if you receive or read out 0, 1, 1, you say, well, this is most likely meant to be 1, 1, 1. Okay. So how many errors can this correct? What? So, but if they were all, let's say, out of the block of 3, so you take a 1 bit like a 1 and you write it into a 1, 1, 1. Of course, if they're all flipped to zeros, you're not going to know, right? So, in fact, if 2 of them are flipped, you're still not going to know. You're going to decode incorrectly. So this will correct 1 bit out of the 3. All right, so here's another way to write the code is that you have information here, and you have a code word that it gets written to. All right, so if the information was a 0, it becomes 0, 0, 0. If it was a 1, it becomes 1, 1, 1. That's the whole code. Okay. So, and this corrects a single error. Now I'm going to give you a more general encoding mechanism for doing single errors. That'll be a little more fun in a moment. But what if we wanted to correct 2 errors using repetition? What might we do? So this was repetition 3, 1. What might we do if we want to correct 2 errors after encoding? There you go. Let's try repetition 5, 1. So we're going to just repeat 1 bit 5 times. So now the encoding here is 0 goes to this, 1 goes to this, and now we can correct up to 2 errors, right? Now there's a trade-off with encoding with more redundancy. We've effectively reduced our rate of storing information or of transmitting information. Here we only transmit 1 information bit and we used 5 transmissions, right? So it's we would call this a rate of 1/5 for the 5, 1, or a rate of 1/3 for the 3, 1. So you correct more errors, but you decrease your rate of storing the information. We'll look at that trade-off in a minute. So now let's look at a more fun way that kind of gives you an idea of how error correction codes, and there are many of these, and it's a fun topic to study. Let's just see how they can be a little more sophisticated. And to see that, let's look at the Hamming code. Okay, so who has seen Hamming codes? We have one. We have maybe another one. A couple people. Most of you probably haven't. All right. So the Hamming codes are a family of codes that can correct 1 error out of however long they encode into. All right. So it's a whole family. It depends on, it's a parameterized group of codes. Sort of like repetition was parameterized. You could repeat as long as you wanted. All right. So the fun one to illustrate how it works is this length 7 Hamming code. So I'm going to encode 4 information bits to a length 7. And what that means is, say I'm given, the way I'm going to introduce this code is through a picture. Because there's a nice picture that shows you how you do the encoding and decoding. All right. This picture is just looks like a Venn diagram of 3 overlapping circles. And what I'm going to do is I'm going to label this D1, D2. So notice there are 7 segments here if you don't count the exterior. And I'm going to label these as D and P. D stands for data, P is parity. Okay, so what this means is this. Out of these 7 segments, you stick your information in the ones labeled D. Okay, so you're going to be given 4 information bits, something like this. You're going to be given 4 bits, and we'll label them D1, D2, D3, D4, the error correction code is going to calculate 3 more redundancy bits from those. And I'm calling those P1, P2, P3. Okay, and how are they calculated? Well, each circle is designed to have even parity. Okay, so these 4 bits have to have an even number of 1s, and these 4 and these 4. Okay, so you can calculate which parity bits you need from that. An example will suffice here. Let's say that I have 1, 0, 1, 1. Okay, to figure out the parity that I need, I'm going to put that in my diagram, 1, 0, 1, 1, and I'm going to say now the parity bits, this first parity bit should be a 0 to make that an even number of 1s. This one should be a 1, and this one should be a 0. So I could fill these in. 0, 1, 0. Now I've encoded. I've added. That's the redundancy. All right. Now, the cool thing is, if there's a single error, we can find the error because any error here is going to mess up one of the parities, one of the circles. It might mess up more than one. We can go check which circles have incorrect parity, and we know that the error bit has to be the spot that's in both of those circles and not in the remaining circle that's correct. Okay, yes? Yes. So if the error was in any of the bits, even the parity bit, so it sort of treats all bits equal, and it can correct any single error. So if the error was, say, here, then that's going to be the only circle that has incorrect parity. So you know it was the parity bit that's in error. Okay, let's do this as an example. Does somebody want to step outside who thinks they can decode this? Someone who thinks they could decode if there was an error here. I know a bunch of you think you can. You're just not. You want to do it? Okay. Go step outside for a minute. We'll go get you. I'm going to erase these bits. Oops. And great. Okay. Now this is the easy part. Someone needs to give me four bits. Okay. We'll do red here. Give me 4 bits. Oops. I'll do it. Oh, well, I did it in the wrong order. Okay, 0, 1, 1. Am I too loud? Didn't he hear me? Okay. Hopefully he didn't. All right. Now, let's fill in the parities here. Right. So, all right. Now, one of you point to a spot to create an error. All right. So I have a volunteer to pick an error. Anybody? This is very easy. Yeah, where do you want the error? D4? All right. See if my eraser can get me in there. Nope. So that was, so it goes to 0. Okay. All right, let's get him in here, see if he can correct it. We should get back our data, which was 0, 1, 1, 1. Right. You can come back in. So there may or may not be a single error here. Can you tell us what?
Well, the first circle is only 1, 1, so there has to be an error somewhere in that circle. There's also 1, 1 into the second circle, and there are 3 1s in the third circle. So if we change the central bit D4.
Great. So the error is in D4. Very good. Good. So we know that we could correct the error and then pull our information back out. 0, 1, 1, 1. Okay. Is that clear? So I'm going to put a little X there to show that was an error. All right. It was really 1. Okay. So the capabilities of this Hamming code, as we claimed they would be, can correct up to 1 bit of error. Now, there's some we can look at actually some properties of Hamming codes. First of all, let me explain that this the family of Hamming codes looks sort of like, I'll give you a chart. This may or may not make sense at first. It generalizes. You can always make Hamming codes of size for any k. you can do, there's always a Hamming code of size 2 to the k minus 1. Okay, with the where the redundancy is k bits. Of course, the number here is not the redundancy, that's the amount of information, so I take the difference, right? So it would be 2 to the k minus 1 minus k would be how much information. So that doesn't look so pretty, but just think it has k bits of redundancy and has 2 to the k minus 1 in length. Okay, here k is 3, right? And it always corrects a single error. And the parity check, we can instead of using circles, for different k, the circles aren't as pretty anymore. But I can just make a chart of what the parity check is. And you have, let me put the bits in a different order. I'm going to say you have the first parity, followed by, and then you have second parity followed by a single data bit, D1. Then you have the third parity followed by 3 data bits here, D2, D3, D4. Now this may not look like a good pattern, but it actually is, because then I'd have a fourth parity followed by 7. Okay, so it's 2 to the, it's a power of 2 minus 1 is how many data bits I put in between each parity here. All right, but this corresponds with the Hamming code we just looked at. The pattern for the parity checks are, imagine the 0 column is missing. You do every other bit is in the first parity. Okay, here's the second parity check is skip 2 onto, skip 2 onto. Whoops, there I didn't skip 2. Skip 2 onto. I said skip 2 first, but I'm imagining there's a column there that's missing. Okay, and then the next one is skip 4 on 4. Okay, so it's really just, if you look down the columns of these are this is just counting in binary, where this is the least significant bit, next significant bit. You have a 1, a 2, a 3, a 4, a 5. Okay, so anyway, it's a simple pattern. But notice that these parities match up with these circles, right? This first parity check, it says add the sum of these bits should be 1, mod 2. All right, that means they should have an even number of 1s. And what are these bits? That is this circle here, right? And this next one is the P2 circle, and the next one is the P3 circle. Notice that this pattern will only include one of the parities in each of the in each row. So if I wanted to find the next Hamming code, I would do another parity. You could call that P4, and I would then do a bunch more data, 7 more data bits. And then I would extend this pattern out. So this first row would have some parities that cross into there. This next one would do that. The next one would be like that. So you get, and then there would be a new parity check that would be associated with P4 that would be like this. Okay, so there's a construction for Hamming codes. I'm not going to argue why you can always correct a single error, but you can. All right. So it's an interesting family of codes because it's easy to understand. It's nice to demonstrate. It's been known for a long time, even before information theory was around, even before the understanding how well error correction codes can work. This has been around. But it's not a very versatile family because it only will ever correct a single bit of error. And when you get very long sequences, you may expect more than one error in the sequence. And these can't handle that. In fact, Hamming codes not only can't handle that, but if there's 2 errors or more, it's going to decode to the incorrect information. It's not even going to tell you there's an error. It's going to decode to an incorrect value. Okay? Because there's a certain property of these Hamming codes. Let's talk about how error correction codes work in general, not just Hamming codes. So imagine that we have this. This here is the space of all sequences of the length that we've encoded to. So in this case, 7-bit sequences, binary sequences. Okay, so what we have is there are 2 to the 7 possible sequences here, but not all of them could have been the result of an encoding. Okay. In fact, how many different encodings do we have out of this space? So this space is size 2 to the 7. How many possible encodings do we have? Well, there are only 4 information bits. Those are your degrees of freedom, right? So there are 2 to the 4 possible ways of encoding here. The last 3 are calculated from the first 4. So we can say in this space you've got code words. So you have, a bunch of these things, and I'm going to say there are 2 to the 4 code words. So the idea of any error correction code is out of the space of all sequences, you pick some subset that are your valid transmissions. If you receive one of those, you assume there's no errors. But you may receive something that wasn't a code word because of the errors. Now, if you want to guarantee you can correct a certain number of errors, like in this case, you want to guarantee you can correct up to a single error, then what that means is that no other code, that around your code word you have a ball. A ball measured in what we call Hamming distance. That means how many bits do you have to change to get to that point. Okay? And for this case, we have balls of radius 1. That means if you take all points that are Hamming distance 1 away from your code words, those are everything you could get with a single bit error, right? These Hamming balls do not overlap. If they don't overlap, then you can guarantee that you correct up to the radius of that Hamming ball, a single bit error, right? So that's what it means to be able to guarantee you can correct. So any error correction code that gives such a guarantee, if it can guarantee it can correct 3 errors, it means Hamming balls of distance 3 around your code words do not overlap, right? Now, often when you design error correction codes, in between these Hamming balls, there's a bunch of space. There are sequences in here that aren't within any of those balls, okay? It's just part of the design of your error correction code. You couldn't pack these close enough or whatever. There are a few exceptions, and Hamming codes are one of the only cases where you have a so-called perfect code. And this name perfect code has a specific meaning. It means that these balls are packed perfectly efficiently. So it actually means there's no gap in between these balls. Okay, so that has certain implications. It's very rare. But it also has certain implications. It means if you take an arbitrary 7-bit sequence and fill it in here and pass it to some Hamming decoder, okay, it's always going to be able to find a valid code word within a single bit error of that sequence. No matter what sequence you give it, it'll be able to decode and say, oh, that was supposed to be this information, and there was a single error. Okay, so it's not able to do error detection, for example. If it had gaps here, you could at least say, if the sequence is in that gap, that it's an error, even if you can't decode which one it is. Right? Okay. Let's do a little analysis of the codes we've seen and what we might care about in terms of performance. Okay. So let's look at a situation where we have some sort of simple model for how errors occur. So we're going to use a pretty standard model. We'll use the binary symmetric error model. So the binary symmetric channel, this is called. Usually when you model noise, you often call it a channel. Okay. So what this means is that suppose you actually are writing your information in bits, like everything we've been talking about so far, and that each bit independently has an error probability, has an error with probability p sub b. So we have some number, maybe it's a tenth, whatever, that defines the noise. And it means that each bit might get flipped with probably 1/10 independently. Okay, so then we can look at our codes we've seen. We can look at, let's say, the repetition 1-3 or 3-1. Okay, And here, what's the probability of error now that we get an error if we have 2 or 3 errors out of the 3 bits. Okay, that's exactly the case we get errors. So probability of 2 errors plus the probability of 3 errors. All right, now that's going to be, there are 3 ways to get 2 errors, so 3 times, and then any one sequence that has 1 error and 2 correct. By independence, we say, well, for example, what's the probability that the first 2 are in error, PB squared, times the probability that the last one is not an error, 1 minus PB. Okay, so the 3 is just accounting for the fact that there are 3 ways to put 2 errors in there. So that's the first term, and the second term is the probability that there are all 3 errors is PB cubed. Okay, so there's an exact thing for the error probability for that Hamming code. Now let's look at the, sorry, that was the repetition code. By the way, repetition, if you look back at how I said to generalize Hamming, I said you could do a Hamming code for any 2 to the k minus 1 length. If you let k be 2, then that's a Hamming code of length 3. And the redundancy is 2. So you have 1 information bit you're encoding to length 3. It turns out repetition 3.1 is a Hamming code. It's the first Hamming code. Okay. But the other repetition codes are not. Okay, so here the probability of error is, again, it's, well, now we could say it's 1 minus the probability of having 0 errors minus the probability of having exactly 1 error. All right, and we can write out what those are. That's 1 minus the probability of having no errors. All of them have to be correct. That's 1 minus PB to the 7th power. And then 1 error, there are 7 ways to have 1 error. You would have 1 bit in error, that's the PB. You would have 6 of them not in error. Okay, now in both these cases, now you might want to simplify this just to get some understanding of approximately what's the ballpark for how much error there is here. And this is on the order of 21 PB squared. Why is that? Well, because if you multiply out this first term to the 7th, you get a bunch of binomial coefficients. If I drop everything that's PB to a higher power than 2, then this is what I would get. So this approximation just drops off things of order PB cubed, PB to the 4th. If the bit error probably is small, this is going to be a good approximation. I mean, similarly up here, we could say, well, look, everything here is PB cubed except for this first thing. So this, you might say, is approximately 3 PB squared. Okay. Now, let's compare these on a graph, and I'll give you an idea of what information theory has to say about error correcting. So suppose, for example, that we have 0.01, very small bit error probability. Okay, that's a chance that any 1 bit is in error. And we make our same table here. We say, here's the probability of having error after decoding with your code. Again, I'll write out my 3 codes here. This, yep. Oops, repetition 3.1, Hamming 7.4, and the last one will be uncoded. That means just send your bit. Don't worry about error correction. So we'll call that a 1.1 code. All right. Now you plug these in, and you get that the error probability is 0.000298. For the repetition. For the Hamming, it's 0.00203. And for the uncoded, it's just exactly PB. You get that probability that there's an error. Now we see that the more redundancy we add here, the better error correcting capabilities we have. So let's put it this way. Let's look at a trade-off between rate of the code. I can write here what's the rate of each of these codes. It's very simple. It's just the repetition is a rate of 1/3. You get 1 information bit per 3 written bits. The rate here is 4/7, and the rate here is 1. Okay, so Lower rate means you're adding more redundancy. Okay? It's like the efficiency of transmitting your information. So what we have is you can't get more than a rate 1 in a binary code. And let's put on this axis, let's say this is the probability of error. And we know 1 point already on this trade-off. We know that for rate 1, we can get, whoops, that's not 0.1, it's 0.01. So we know we can get this point, right? Just unencoded. Now the repetition code has a rate of 1/3, and it has an error that's very small there. It's 2% of that, right? 3% of this height. So something very low here. So that's the performance of the repetition code. We know that the Hamming code, let's see, 4/7 here. And it's getting, oh, what happened? And it's getting an efficiency, it's like, 2/10 of this height. So it's like this. Okay, so there's a plot of the performances here. Now what you might really like to know is, of course, we like things to be down and to the right in this plot. High rate, low error. And we might want to know what are the fundamental limits. If you consider all possible error correction codes, how low can you get in that direction? And that's really what information theory answers. And Shannon, in his 1948 paper, actually just completely tackled this question in an unexpected way. Because up to that point, there was sort of maybe a belief that in order to get low error probability, you would have to go to more and more redundancy. In other words, that maybe if you looked at the fundamental trade-off here, you might get something. Let's say yellow represents the space of performance of any viable code. We know we can do this. Right? And we know that we can keep making longer and longer repetition codes that give us lower and lower error probability. So no, if we keep going to lower and lower rates, this should go towards 0. Okay? And the belief was sort of like maybe that is the lower envelope of this performance curve, which isn't true. So what Shannon showed is, in fact, there is a point. For this particular channel, the point is actually way up here. And you can actually design error correcting codes that get you arbitrarily small error and get right up to this particular rate, which has become known as the capacity of the channel. So there exist codes, maybe they won't give you exactly 0 error, but they'll give you as small of error as you ask for, and they'll have rates that are right up to this value. So the real envelope looks like something that comes down like this and follows the x-axis here. And so in reality, you can find error correction codes that give you performance anywhere up to there. Now, what we care most about is getting arbitrarily good reliability. We don't care about operating up in these points. We don't care about operating up here with non-negligible error. We care about having negligible error in our communications and getting as high a rate as possible. So this becomes the important operating point. It's the capacity of the channel. That was defined again by Shannon. He said, hey, there is a capacity, and you can get reliable communication up to that capacity. The capacity is going to depend on your noise model. We have a particular noise model here. We have a binary symmetric channel, and we have a bit error probability, 0.01. Turns out for that particular channel, the capacity happens to be this. Okay. In fact, there's a formula. I'm not just, this isn't like some important example of a channel. We have a formula for the capacity of any channel. And that also comes from Shannon. The formula, and so for the binary symmetric channel, when you specify that formula for binary symmetric, you end up finding that C is 1 minus PB log 1 over PB, minus 1 minus PB log 2, 1 over 1 minus PB. Now there's a remarkable observation here. In general, so this is a specific capacity formula for binary symmetric channel. Okay. In general, the capacity depends on entropy. There's that magical entropy that we saw in compression. Okay. Turns out that the entropy of the noise in a specific formula gives you the capacity of the channel. And so you might notice here, this whole thing here that I'm subtracting off, we defined in a previous lecture the binary entropy function. This is the binary entropy function. So the 1 minus the binary entropy function of the noise is exactly the capacity for the binary symmetric channel. So I plotted the binary entropy function previously, and here I'll plot 1 minus it. So we have that C as a function of the noise probability. PB, here's 1, here's a half noise probability. So the capacity is going to be like this, and where it maxes out at 1 bit. Okay, you can't have a capacity more than 1 bit, even for a noise-free binary channel, right? Okay, now this may surprise you. It's not monotonic. In other words, it doesn't just keep getting worse as the bit error probability gets higher. Why is that? Why does it have this symmetry? Yeah.
After there's more than a 50% error, you're essentially flipping like more bits than you would be.
Yeah, so just treat them opposite way. For example, imagine the case where you're at probably bit error 1. There's really no noise. You know every bit was flipped, and you just have to flip it back. So you still have full capacity. Okay, so so that's it for error correction. I'm now going to, any questions about that? All right. Okay, let me mention, we've talked about now, so we're briefly covering a lot of the main, just barely introducing a lot of the main topics of information theory. We did lossless compression. Now we've done something about capacity and error correction. There's another topic which actually is important to information theory, and that is secrecy, meaning like private communication. You want to send a message, you don't want someone else to read it. Okay. Now, it may surprise you that, well, first of all, maybe it won't surprise you. You're used to encryption. You know that you can do some encryption, and that keeps people from reading your messages. If you're familiar with encryption, you'll know that the encryption actually used in technology is not giving a theoretical guarantee of secrecy on the level that no one could ever get your information. What it's saying is that unless, short of doing exhaustive search, we don't know any fast algorithms for decoding, and exhaustive search is way too hard to do with the size of space we're dealing with. So in other words, encryption, in principle, if you had a long enough time, you could break encryption algorithms that are used, that we use on the internet, say to encrypt your credit cards. But this secrecy I'm going to talk about right now is one that no one could ever break. It does not a matter of computation or how much time you have. It may be surprising that there is a way to communicate in public, let everyone hear your communication, yet have only one person in the audience get any meaning out of it. And the way to do this is the one-time pad. So this requires that you set up your situation beforehand, that both of you, let's say before I ever had any information I wanted to communicate, I set up with another individual a secret key. We sit here and we flip coins, 1,000,000 times, and we write down the outcomes, and then we never share it with anyone else. Okay, so if we can verify that we're the only two that know the key, then in the future, when I actually have something to say, I can just post it on a website or whatever I want to get the message to you, and I can guarantee that I do it in perfect secrecy, under constraint that the message I'm sending is no more bits than the length of the key that we had set up beforehand. Okay, so it's neat that perfect secrecy. So this gives perfect secrecy, and I'll show how you do it. It's very easy, but it's kind of cool that perfect secrecy or perfect privacy actually does exist. That you can do such a thing, and the way you do it is you have your key bits. These should be random and unknown to everyone except the parties involved. And what you do is you write your message in bits as well. Okay? And let's say here are some message bits. As long as you're, and so have these both be the same length. So like I said, we have to have at least as much key as the message we're trying to transmit. Okay? you do an exclusive OR, which is the same as a mod 2 sum, or a binary sum, of each pair of bits that are lined up here. So do an XOR. That's going to get you a result down here. Like the XOR of those two is 1, 0, 0, 1, 0, 1, 1, 0, 0, 1. There. I did a bitwise exclusive OR. This is what you transmit. This is what you don't worry at all about who gets to read this. You just need to somehow get it over to the one who needs to receive your message. How is he going to get meaning out of this? Assuming the other person knows the key, what will they do? Yeah? What were you? Exactly. You want to reverse this, and the reverse is exactly the same process. You just, again, XOR. So the decoder does XOR as well of the transmitted message that they received and the key. And that'll get you back the message that you want. Okay. So we know it can be decoded. Now I'd like to mention, what does it mean to have perfect secrecy? How do we know this is truly perfect? I mean, you sent something that had to do with your message, right? Well, probabilistically, we know that perfect secrecy means, what perfect secrecy means is that the message is independent from a probabilistic point of view of the transmission. Okay, so independence, we said, was that these are both random, right? The key was random, so the transmission is going to be random. Independence means that the joint distribution is the product of the two distributions. If you can verify that, which is easy to verify. Often I do that here in the lecture, but I maybe would rather do something else. Let me give another definition for independence. Another way to verify independence is that the probability of the transmission of what you transmit given the message, so for any particular message value, the probability of what you transmit is random because the key is random, that this conditional probability has to equal the unconditional probability if you didn't see the message. Turns out that's enough to verify that they're independent. So if you can, and you can check that this is true because the bits are equally likely. The key values are equally likely to be 0 and 1. Okay, so you can check that, in fact, this equality holds. That no matter what message you're encoding, no matter what bit your message is, the key is equally likely to be a 0 or 1, therefore the transmitted bit is equally likely to be a 0 or 1. Okay, for each bit. And since these are independent of each other. Okay, so this is actually, has been used. It's been used correctly and incorrectly. For example, even dating back to, say, World War II, it was known that this is secrecy, but it's also known that you should never reuse your key. As soon as you go reusing your key, you do not have a proof of secrecy anymore. But keys are expensive to generate, right? So there were cases where certain countries were reusing their keys, and then the code was broken. All right. Now, you might say, well, gosh, if you need a secret key of this length, how can that be any easier to establish your secret key than just to communicate in private to begin with, right? I have to somehow get you a key that's as long as my message. Isn't that as difficult as it would be to just find a private room and tell you my message? All right. Turns out there are ways of using technology to establish keys, in particular using quantum mechanics. There's a quantum key exchange that allows you to essentially transmit a key and check if anyone has seen it. Okay? Now that's the benefit you get from doing encryption like this. Suppose I get an armored truck and I load it with hard drives and I send it across to whoever I want to send my message to. That's a way of trying to send a secure message. If it gets intercepted, then I'm stuck. They have my information, right? If instead I load up a hard drive full of random bits, okay, and I send that, no meaning to these at all. If it gets intercepted, as long as I know it was intercepted, I just throw away those random bits and do it again. Load up another truck with random bits. As soon as I get one through, now I have a key established. I have this tunnel, this secure tunnel where I can communicate and know that my information is perfectly secure. And that's what the quantum key encryption allows you to do. You send garbage through this quantum channel, and you know whether it's been read or not. And as soon as you're in a situation where it's not being read, you use that as your key, and you send your real information. Okay, so that's basically what I wanted to cover. I had another example. The last topic of are we already at 9:50 here? Oh, we have 3 minutes. All right. The last topic of really that information theory addresses is compression that's not lossless. Okay, we've talked about lossless compression, but actually there's some theory about how well you can compress if you want to limit, like JPEG, right? JPEG limits the number of bits, but doesn't give you back the exact information. It gives you some corrupted form. And there's a fundamental trade-off between the number of bits you use and the quality of your reconstruction. In fact, it's a very nice trade-off. It looks a lot like the trade-offs you get for channel capacity. And the one example I want to give, you can think about it on your way out, is just kind of a fun example to show that if you do this cleverly, you can save more bits than you expected, even getting a high-quality reconstruction. So imagine that you have, so I'll call this a puzzle because we won't have much time for it. You have n-bit information sequence, and you want to compress this, okay? You want to describe it with a certain number of bits, less than n. But what you're allowed is that after it's been decoded at the other end, you're allowed to have a single error in your n-bit information sequence. So think of this like an n-bit, binary pixels, and you're allowed to put in one error. You don't want an error, but you're allowed to do it because that's going to be the cost of compression. Okay. Now, a single error is not much out of n, so we're not going to expect to get a lot of savings here. This is kind of an edge case, just as an illustration. All right. How many bits? So how much compression can you get? In other words, the transmission. So we're going to allow one bit error. How many transmitted or stored, how much, I'll call it transmission, how many transmitted bits needed? And of course, the answer is going to be close to n, so it's n minus what? In other words, how much do we save? Okay. This question might not be sinking in for some of you, so let's just get one possible answer. Can you save any bits in your transmission? What could you do? For example, what? Yeah, just don't send the last bit. And they could just guess that it's a 0, and they might be wrong, but you're allowed one error. So you definitely could at least compress it by saving one bit. Just don't send one. Or if you care more about averages, if you want there to be one error on average, maybe save 2, right? Because they could guess zeros and they'll maybe get 1 right. Okay, that's still not much. I want to save more than 1 or 2. Turns out you can save considerably more. And in fact, you can use something we've talked about in this lecture in a weird way. I'll even tell you what you can use. You can use the Hamming codes in a weird way here to save considerably more than 1 or 2 bits. In fact, you'll save. Anyone want to guess the order of how much you'll save? No, not binary entropy. Some function of n, some monotonic function of n. So you'll save log n. Might be log n minus 1. Doesn't matter. You'll save roughly log n bits. Okay, and yet only cause at most 1 error. So you can think about how to use a Hamming code to do that. It's kind of fun. It's not hard, but it gives you an illustration of, first of all, there's a duality between error correction and compression, and secondly, it gives you a kind of a hint that, yes, if you're clever, you can actually compress a lot and not lose much in terms of quality. And that's the magic of this trade-off for lossy compression.